Hello everyone, this is a session for SQL Bits called Getting to Know SQL Server Encryption Capabilities. My name is Mladen Prajdic and I'm a data platform MVP from Slovenia. I've been an MVP for 10 years now. I've been working with SQL Server for 15 years now. I've been working with .NET since its first version, and in my free time I work on an SSMS add-in called the SSMS Tools Pack. So, what are we going to talk about today? First, we're going to have a quick terminology refresher, what the actual terminology we're going to be using when it comes to encryption. Then we'll take a short look at transparent data encryption. We'll take a look at how to secure communication channels like SSL and TLS to communicate with SQL Server on. We'll talk about symmetric and asymmetric server encryption, and in the end we'll talk about the always encrypted capabilities of SQL Server. So, to start, a quick terminology refresher. In SQL, not in SQL Server, but in general, we have something called cryptographic functions, and we have a possibility of symmetric encryption and asymmetric encryption. Now, in symmetric encryption, we have a single key that is used to encrypt and decrypt the some text, right? Some value. There are a few algorithms that we can use. They're called DES, triple DES, AES, but other than AES, most of them are all old and quite deprecated. In asymmetric encryption, however, we have two keys, a public key and a secret key. Basically, we encrypt with one and decrypt with another. It's much slower than symmetric encryption, and it's usually used to securely exchange symmetric keys. Then we have something called hashing. Now, hashing is a one-way irreversible function, unlike encryption, which is a two-way function that can be reversed. Hashing, however, is irreversible. There are also quite a few algorithms out there for hashing, like MD5, SHA-1, SHA-2, SHA-3. However, from SQL Server 2016 onwards, all algorithms other than SHA-2 and SHA-2 are deprecated. So basically, if you're using anything like MD5 or SHA-1, you should think about changing that, because in future versions of SQL Server, they might not be supported anymore. Then we have something called an HMAC. Now, this is a hash-based message authentication code. Basically, what it does, it verifies both message integrity and authentication, right? So the way it's calculated is you take your encrypted ciphertext, you prepend your key to it, and you create a hash out of that string. Then you take that hashed string and you again prepend your key to it, and then hash everything again. And that way you calculate your hash-based message authentication code. Now we have two types of encryption, deterministic and randomized. Now, deterministic encryption, basically if you take a plain text, you always get the same ciphertext. That's why it's called deterministic. Now, the benefits of this are they can be indexed, they can be joined, they can be grouped, and they can be singleton looked up. Meaning, they are also vulnerable to statistical frequency attacks. So if you have a column that has very few unique values, like true, false, or male, female, or countries or territories, etc., it's relatively easy to create a algorithm that will, with high probability, guess what those values are, right? For example, in this graph, we have a typical distribution of letters in an English language text, and we can see that letter E is much higher, it occurs much more often than, for example, letter B. And you have for example, countries in your database, and they are encrypted with deterministic encryption. And your major client is, say, in the United States or in the UK, you can guess that from that data. You don't know the actual value, but you can guess it with high probability of being correct. Now, on the other hand, randomized encryption, you take a plain text and you always get a different ciphertext. So you always get a different value when you encrypt it. Statistically, it looks completely random. Can't be reverse engineered, of course. The two things that are public in this encryption mode are the public ciphertext, of course, and the IV. Now, IV is called initialization vector, and it's basically a random sequence of values that are the input to the randomized encryption algorithm at the beginning. Now that means that there is no indexing, there is no joins on it, you cannot group on it, etc. There is no singleton lookups, there's none of that. Now the visual difference, it's sometimes when we talk in abstracts like this, it's interesting to show a visual how it looks, right? Now on the left side you have the original image that's not encrypted, of course. In the middle you have an image that is encrypted with deterministic encryption, and you can see that you can still guess what the what's on the picture. You cannot get all the details, but you can still guess what it is, right? Now the completely random encryption, right? You cannot guess what's on the picture at all because it looks completely random. So to get to the SQL Server part of things, first we'll talk about transparent data encryption. Now one of the first questions I get when talking about TD with various clients is they ask me, does this encrypt communication channels, meaning is the data encrypted over the wire? And it's not the case, right? So the transparent data encryption does not provide encryption across communication channels. That is the job of SSL and TLS that we'll take a look at in the next point. What it does is it encrypts data at rest. So basically it encrypts data on the disk. The data is encrypted when writing to disk and decrypted when reading from disk, right? So if you plug your disk from your computer, somebody steals it, for example, they will not be able to decrypt that disk without proper keys, right? That's the whole point of transparent data encryption. When it comes to working with SQL Server, the transparent data encryption layer is completely invisible to you. Basically, you don't know that transparent data encryption is on behind the scenes. So anything in memory, however, is clear text. So any data in the buffer cache is in clear text. So what's the point, right? As we said before, if somebody steals your physical drive with the data, but not disk with the OS installation, where they can reverse engineer the keys from, they won't be able to get to your data. Now, if you want to see how hard or how easy it is to break TDE, you can search YouTube for breaking Microsoft SQL Server Transparent Data Encryption video, and in this video, the gentleman who created the video shows how to get the password from your OS disk. Meaning, if your data is on the disk that's not installed on the same one as your OS, they cannot get that password back. Or you can always use a hardware security module where the keys are not actually stored in your OS, but they are stored in the security module. So how do you enable this? It's actually very simple. You have to create a master key encryption. You can use a password there. You have to create a certificate for it, and then you basically just say create database encryption key, encrypt by server certificate, and set encryption on the database, and that's basically it. And behind the scenes, the TD gets enabled. Okay, so next one is how to secure your connections. So how to encrypt your connections to SQL Server and from SQL Server. There are basically two ways you can play with this, right? For SSL, if you are required, so if you want to encrypt all connections that come to your SQL Server, so you say there are no exceptions, everything has to be encrypted. It's very simple to do. You just say on the SQL Server instance in SQL Server Configuration Manager, you say force encryption equals to yes, and no client change is required. So the client, when it tries to connect to the SQL Server, it will see, okay, I have to support encryption. The client driver will communicate with the SQL Server driver if they can negotiate the correct exchange algorithm for the exchange of keys. And if that is not possible, the connection will fail. If it is possible, the connection will succeed. Now, if you want to filter those connections, so if you just want some clients to connect to SQL Server encrypted, you can just do that as well. So on the server, you have to say encryption is an option, and then in the connection string on the client, you have to say encrypt equals true. However, in this case, you have to take the public key of the server and you have to install it on the client, right? So you have to install that public key on each client, and you have to trust that server certificate for communication, because in the first point that we talked about, if it's required by the server, so if it encrypts all connections, the server says, okay, I have to have all connections encrypted, so here's my public key, and basically it sends the public key to the client, which the client then uses to negotiate the SSL exchange. So the actual certificate on the server, on the SQL server, it can be a certificate authority certificate, or it can be a self-signed certificate. The security between the two, when it comes to encryption itself, it's the same. It just, if you have a certificate authority certificate, that means that you have the whole chain of certificates up to the trusted certificate authority, right? So you know who issued that certificate. And if you want to check if your connection is encrypted, you can do that by checking dmv sys.dm exec connections. The column is called encrypt option, and if it's encrypted, it's 1. If it's true, if it's not encrypted, it's false. The other way you can encrypt communication is by using IP security. So both client and server OSs must support it, and you basically just check a checkbox saying I want to use IP security, and they negotiate the encryption between them. So how do you encrypt? How do you enable SSL and TLS in SQL Server Configuration Manager? Basically, you go to SQL Server Network Configuration, you go to protocols for your instance, and you say force encryption equals yes, and on the certificate tab you choose your certificate, and that's pretty much it. This is for when you want to enable the encryption for all connections. Okay, so the newest version of TLS that's basically out in the wild is, and it's hopefully mostly used now, is 1.2. And SQL Server 2016 and up, they all support TLS 1.2. However, if you're on a lower version of SQL Server, you can enable TLS 1.2, but there are certain things you have to install, right? So for other versions, check out the support article from Microsoft called TLS 1.2 support for Microsoft SQL Server, and there you can see all of the requirements you have to do for each version of SQL Server. So next up, symmetric and asymmetric server encryption. So we'll talk about the asymmetric encryption first. We have a few functions in SQL Server called encrypt by asymmetric key, encrypt by certificate, sign by asymmetric key, or sign by a certificate. Now, both certificates and asymmetric keys simply serve as wrappers over the RSA keys. They are slow and they are used for encrypting small data. So you would not use asymmetric encryption to encrypt a whole column of data, right? Because if you have a lot of text in your rows, so this would take a lot of time compared to symmetric encryption. Right? Now, symmetric encryption, on the other hand, you have encrypt by key and encrypt by passphrase. I would suggest you don't use encrypt by passphrase anymore, because behind the scenes it uses triple DES algorithm, which is basically just a DES algorithm applied 3 times, and DES has been shown to be relatively weak for today's standards, so don't use it. Now, here we have a simple table with an ID, with a title, and an encrypted salary, right? What can we guess from this table? We can most likely guess that a CFO, so Chief Financial Officer of a company, most likely has a higher salary than the DBA, right? And the DBA most likely has a higher salary than the junior DBA. We of course don't know what their salaries are, but that's really not relevant. Now, how would we be able to break this, right? If we would get access to this table, we could say update the salary of my junior DBA with the value from the DBA. So we would put the value of the DBA salary, the DDF, GES, etc., into the junior's DBA salary. Now, if you didn't have any other mechanisms of checking if this is correct or not, you would not know the difference, right? When the column would get decrypted, the salary between the junior DBA and the DBA would be equal, and nobody would know if the junior DBA simply has amazing negotiation skills for their salary, or the DBA has really bad negotiation skills for their salary, right? You, of course, wouldn't give the junior DBA the salary of a CFO, because that would be a bit suspicious, right? Now, to guard against this kind of attack, we would use something called the authenticator, right? So this kind of attack is called a whole value substitution attack. Now, what the authenticator does is when you encrypt the salary column, right? For each row, it will take an additional parameter called the authenticator, and that parameter, in our case, will be the ID, because the ID is primary key, and usually you don't change the primary keys. So in this case, right? So when we encrypt the salary for the DBA, we will say encrypt our actual salary, use the authenticator 529, and this will give us the result of DDF, GES, etc. When we encrypt the junior DBA's salary, we will use the 352 ID, and we will get its encrypted value. Now, if we were to substitute those two values, when we actually substitute them, nothing will happen, right? There will be no error, no nothing. But when somebody starts to decrypt the values, they will have to, because when we encrypted the value, we use the authenticator, they have to decrypt the value by using the authenticator as well, right? So when they get to junior DBA salary, which would now be the DDF, GES, etc., they would use the authenticator ID of 352. And because that is different of the 529 for the DBA, it would fail, and it would get, it would throw the error, right? In this way, we would know that the values somehow are wrong, and we could go and investigate what happened, right? So this is something we have to be especially careful about when we're using symmetric encryption, and always use an authenticator. I have seen a lot of places that don't use authenticators simply because they didn't know this exists, and they didn't know you could use such an attack, right? And it doesn't even have to be an attacker an outside attacker that would do this. You could have, actually, you could have an update permissions of the junior DBA could have update permissions on this table, and would basically change its salary, be quiet for, I don't know, half a year or a year, and then just quit, and nobody would know, right? So you have to always use an authenticator. So one problem we have when we encrypt our data is basically we lose any kind of high-end analysis over it, right? So we cannot search on it, we cannot basically see it, we cannot aggregate it, nothing of the sort, right? So the only way when we're dealing with server encrypted data is that we somehow have to decrypt the data to be able to do operations on it, right? So how can we speed this up? If we have 1,000,000 rows in our table that are encrypted, and we have to decrypt all of the 1,000,000 rows each time we do some kind of calculation, that is not very optimal, right? So this is a way of narrowing your search, basically your search space. Basically, you partition the encrypted data. So first, you have a message M. So this is a clear text, basically the text that we encrypt, and we encrypt it into the ciphertext C, right? Now, we take a hash of this message. So this is an error. This is not a C, but it should be SHA-256 of M. So we basically take a hash of the clear text. We convert that hash into an integer, and then we say integer modulo say 1000. Now this 1000 is basically the amount of buckets we have, right? So we will basically, or partitions, if you will. Basically, we will partition our data into as many partitions quoted, as we want, so that when we search for some value, we just look into that partition, not through all of the data, right? Now, this partition can be used in a where clause to narrow our search, and this partition can be indexed. And if this seems confusing, I will go through all of this in the demo. Right? So we go to the demo. So this is called a hash bucket search, right? So we will use the database called encryption stuff, and this encryption stuff database has a table of credit cards. Now these credit cards, there are 110,000 of them. They are just basically fake credit card numbers that are still valid credit card numbers when you check the CRCs and perform all the credit card checks, but they don't really exist. Right? So what we'll do is we will take a random credit card number that is at the end of the table, just so that we know that we will have to read through all of the table pages to get to it. So it's not instantaneous. It wouldn't make much sense that we would do a demo where we would search for the first row in the table, right? When it comes to data pages. Okay, so if we set statistics time and IO on, now we take a look and we can see that we have a MasterCard that is ID is 5 nines, and we have read 2,731 logical pages, right? And it took us about 28 milliseconds, which is okay. So count, we have 110,000 tables. We will clear our columns that we will, I will explain what they are later. And we have about 22 cards ending with 8007. Now, why do I say this? Why is this important? Basically, when you, in some credit card processing systems, you have the last 4 numbers are saved in clear text, usually, that you can just check if that credit card, if those 4 last numbers are actually on your card, right? It's just like a personal check thing. So what we'll do is, so we have our data completely unencrypted, like a base table, and we want to move this to encrypt the data with being able to search on it faster than by going through the whole table. So what we'll do is we'll first create a symmetric key. Here I will encrypt it by passphrase, but don't really use it since it's SSS. In proper environment, you would use a certificate to use this, to do this. So I'll create a temporary symmetric key. Okay, so I've already created it, never mind. I will open it, and I will update all of our card numbers I will encrypt all of our card numbers into a new column called card number encrypted. Now you can see that I will use authenticator here, and I will have the card ID as that authenticator, right? So let's create this. So this will take a few seconds, and we'll take a look at how, so it went through the whole table, 2,731 reads, that's fine. And we'll take a look at our credit card, right? So we will have to decrypt all of the credit cards for now to get to our credit card number. Remember, now we're looking at the encrypted column. We are not looking at the clear text column anymore. So if we run this, we have our credit card number, the credit card number encrypted value, and the decrypted is the same. Right? So this is just the check column that we got here. So let's see, we had 2,731 logical reads. It took about half a second, which is not too bad. But you know, if you have a lot of these requests, half a second every basically second, it can crap on. It can get to be a problem for the SQL server. Now, remember when we talked about creating a partitioning function, right? So what we'll do is we'll basically group the data. So we'll take our this is our partitioning function. We'll take our string, which is our credit card number, and the divisor, which is the number of buckets we want to use, and we will create a hash of our string. We will save that into an integer value. Here we don't have to convert the bytes into an integer value because SQL Server does that automatically. And we will return the remainder, the modulo of the value and the hashed value and the divisor. So let's create this function. Okay. Now I will update our credit cards table, and I will, for each card number, I will create the hash group in which that card number is. And I will do that by saying use this function on our card number, and the divisor is 1000. So we want to have 1000 buckets. Meaning, if we have 1000 buckets and we have 110,000 credit cards, we will have about 110 items per group. Which means we will have to only go through 110 items instead of 110,000 items, right? So I will run this. And this query, so this finished successfully, this query will just show us the simple visualization of how the values are actually distributed within each group, right? So you can see basically the number of stars is the number of elements in each group, and you can see that they are relatively evenly distributed, right? There are no any peaks or any valleys that are way outside of other values. So it's about 110. So it goes from like 90 to 120, right? Okay. That means that our values are evenly distributed. So any value that we search for, we will have an approximately equal search time. Okay. So just to make sure, we have our credit card number is in the hash group 760. It's encrypted. So now we are operating with these two columns, right? We don't operate with the card number column anymore. So if we say the queries we will now write is the same as before with the decryption, so we will have to decrypt our card number encrypted value column, but we will filter down the amount of data we have to decrypt with our group, right? And in our group data, we will input the number of buckets, basically the number of partitions, and the credit card number that we are searching for. So this will now should be much faster, right? So let's see, it didn't seem much faster, right? Let's see what's going on. So we still have 2,731 reads. It means it still read the whole table. And we even have like 1.2 seconds of time, which is way worse than before, right? Before we had like a half a second time. Now why is that? Because remember we said that we can index this hash group or bucket group value, which we didn't do. So let's create an index on it. We will create a non-clustered index on that credit card number hash group column. So let's create that index. Okay, and now let's do the same thing again. So you can see that this query is the same as this query. So the only thing that's different is we added an index. So let's run this, and you can see now it's instantaneous. And basically it read 387 pages and it took 2 milliseconds, right? So going from 1.2 seconds to 2 milliseconds, that's amazing change in speed, right? And now you can run this without issues for any amount of time. It won't be a problem at all. So this way we have sped up our search of encrypted credit card numbers by 3 orders of magnitude. Now note that this is only valid for basically equality values, right? Doing this for like values or comparison on text that is not equality comparison will not work. So this is for small encrypted data that you compare equality on. Okay, and just so we have that, we show that we actually have different card number hash groups and different card number encrypted values, so that you know that we don't cheat. Okay, Now we're going to talk about the Always Encrypted. Now, Always Encrypted, I usually, when I speak in front of a live audience, I usually say I will give you a few minutes to read this, but here you can just pause the video. But basically, this is how it works, right? If you have a really secure password or system and it uses a 4K RSA key, etc., and all the top-notch technology, in the end, the weakest link are still people, right? Somebody can always be exploited in some way. That's what security clearances are for, right? But you know, your employees can be threatened in some way, I don't know, with their kids or something like that, with their spouses, their health. People can be made, can be persuaded to do stuff that they usually wouldn't do, right? That's why it's smart to actually remove the chance, basically technologically, that they are able to do this, right? So if you, before when we talked about communication channels, transparent data encryption, so SSL and TDE, about server encryption, the DBA almost always has full permissions to decrypt the data on your SQL server. And this is, of course, a liability for you as a company. If I'm a disgruntled employee for whatever reason, and I want to, you know, get even with the company and then quit, sure, there are legal ways that you can battle this, but those can be long, and why go through them when you can completely disable that path of attack? So that's where Always Encrypted comes into play. Now, Always Encrypted uses just a single algorithm for all of its functionality. It uses the AEAD AES 256 CBC HMAC SHA-256 algorithm. It's a long name, but basically the name tells you what it does, right? So we talked before about the HMAC, the hash message-based authentication code, where it uses that with the SHA-256 algorithm. It uses the AES 256 algorithm as well for the actual encryption. It uses the CBC mode of encryption, which means that it chunks the data into 16-byte blocks, and each block gets encrypted and is then used as an input into the next block, and then the next block, and then the next encrypted block is used as the input to the next encrypted block, etc., etc., etc. Right? So no two blocks, even if they have the same text, are alike. So you cannot get back the original text in any statistically probable way. There are also two modes: deterministic or randomized encryption. Right? So the way it works is you have something called a column master key and a column encryption key. So basically, you encrypt a column. Not a row, but a column. Right? So master keys are never stored on the SQL server. The way it works is when you say I want to encrypt a column encryption key is generated, and the data is encrypted by that column encryption key. That column encryption key is then encrypted by the column master key, and that column master key is known only to the client. So it's not known to your DBA, it's not known to your company, it's known to the client, right? So nobody can decrypt that data except your client who has the key, right? So the Always Encrypted can be enabled via connection string or by settings in the app itself. It needs .NET 4.6, and if you want to have custom key store providers or use SQL bulk copy, you have to use .NET 4.6.1. So how does it work? So basically, the ADO.NET client has been upgraded to recognize when Always Encrypted is used. So this is version 1 on Always Encrypted. And when you have on the server, you have your column encrypted, and your client says, okay, I'm going to search on that encrypted column, which in this case is an SSN. It will say, the user will type in the same website, will type the SSN 11222333, etc. The ADO.NET will take this value it will encrypt it, because remember, the ADO.NET knows what the, basically it downloads the blob that contains the column encryption key encrypted with the column master key, and the column master key is known to the user and the user only. So the ADO.NET client, right, can encrypt the input value with the correct column encryption key. So that it's done by the ADO.NET driver, and that query is sent to the SQL Server. Now notice that the query that is sent to the SQL Server contains the encrypted value, so the ciphertext. Now the SQL Server says, okay, this is the value, the encrypted value I have to search on, and it goes through this table, checks the equality comparison. When it gets the correct result, the one that it found, it says, okay, I'm going to return now the row. The row is returned, of course, encrypted, because the SQL Server does not have the key to decrypt the data. So it will return the encrypted data back to the client, back to the ADO.NET client provider, and the ADO.NET client will then use its knowledge of the master key to decrypt that data and show the decrypted values to the client. So basically, the client computer has this trust boundary around itself, right? Okay, so let's see how this works. So we will have basically a database called AE demo. In that database, we will have a table called users, and it will have user ID, username, user SSN, and user description. And the user SSN will be encrypted, right? Here I will create a column master key with a certificate in my certificate store. I will create a column encryption key based on that that will be encrypted with that column master key, and the encrypted this binary value, basically you can get it with by some PowerShell magic, as I call it, but if you do it through the wizard, it just works. In T-SQL you have to do some getting those values out of the actual certificate. Okay, so I will drop the database, I will create the database, I will create the table, and I will insert two users into it. Now I have to run this with the connection option of Always Encrypted, enable Always Encrypted column encryption, right? So I will use this, okay? Why? So that I can insert properly encrypted values into our user SSN value column. Because if I didn't use the encryption, the column encryption setting, these two statements would fail, right? So let's run this. Okay, so now you see that we have two rows in our table, my name and Chuck Norris. And if we now try to do this same query in a different query window, but let's check if it has the Always Encrypted enabled. It does. Let's disable it. Let's reconnect and say use Always Encrypted demo and run the same query. We will get the user SSN encrypted, right? So here we are using the option of column encryption enabled, and we are using our key to decrypt the user SSN values. Now in this case, SSMS is being used as the client that has a trust boundary around it, right? In an app case, it would be like a Windows app or web server or something like that. So now that we have set up our table, let's check out our app. We will have an amazing app. It's going to be the best app you've ever seen in a demo. See? And we will have three options. We will have no key, so we will query the table by no key, and we get the same values back as if when I showed you in SSMS, where we didn't use the column level encryption option. Now, the result set only option, if I say result set only, I get back the user SSN decrypted. See, but I get both rows. Now, why is this? Let's take a look at the code. If I have. So no key, simple select statement, nothing special there. Now if I say result set only, I say SQL command column encryption setting result set only. This is the option that you have to set to the SQL command in the constructor. And what this does is it will decrypt any values that are returned to the client. But with this option, you cannot do any filtering. You cannot do any where clauses on it or anything like that. It just decrypts the data that came back from the server encrypted, right? And our just to show you, our connection string is nothing special, right? If we wanted to enable the column encryption setting in the connection string, we would say this in the connection string. But I didn't want to do that because I wanted to show you how to do this in app. And you can have this value, you can have it in a config file that you could change on the fly, etc., or have it different for different parts of the application, etc., etc. Now the next one is the full always encrypted, so the one where you can search and everything, right? So if I specify my SSN, I will get one row back. If I specify Chuck Norris's SSN, I will get his back. If I specify nothing, I will probably get a crash or zero count. Now, how does this work? So again, column encryption setting is enabled. You put it into the constructor and you say you have to create a parameter. You create a parameter called user SSN of your SQL DB type. You say you set its value to the value you have, so it's not encrypted or anything like that. And you simply add it to your parameter list and execute the reader. So when it comes to the app, there are not much changes needed at all, because remember, the Ada.NET provider behind the scenes takes care of all this, right? It takes care of all this. So if I would say some other value here, check full AE, zero count, right? Because there are there's no data matching this filter. And you might ask, how does the Ada.NET client know what to use for the column master key and the column encryption key? Basically, there's a stored procedure on the SQL server that the Ada.NET client executes and gets back the blob that contains the column encryption key encrypted with the column master key. Okay, so back to the presentation. Now, the Always Encrypted version 1 happened until SQL Server 2019. There, Always Encrypted version 2 came out. Now, the version 2 uses something called a hardware secure enclave and enables like and range comparisons and pattern matching. Now, the way to do this is by using these secure enclaves, right? But what are they? Basically, a secure enclave is a protected memory space on your SQL server that is not accessed by any other process, and this protected memory space has a direct connection to your enhanced client driver for the Ada.NET that has been updated, where they share your master key. Right? So this communication between the enhanced client driver and the secure enclave is again completely encrypted, and this enclave gets your master key. And if you say in your query, select the star from customers where name like Mladen, for example, but you use a like pattern matching, so not exact values, it will load all of your raw data into this enclave. It will decrypt every row. It will check if that row matches your query, your pattern, and if it does, it will say, okay, this matches, return just the ID, or well, save the ID, and then when it finishes going through all the rows, it returns the matching IDs. And then SQL Server takes those IDs, those matching IDs that came from the enclave, and returns the rows matching those IDs, encrypted of course, to the client. And then the client takes those encrypted rows and decrypts them into plain text that is shown to the user. Right? So what operations are actually supported, right? So if your column is not enclave enabled, there is no advanced support for any kind of comparison, right? If the column is not with randomized encryption, if the column is not enclave enabled with deterministic encryption, so like in the V1 of Always Encrypted, the equality comparison is supported outside of the enclave, like we showed in the demo. Now, if the column is enclave enabled with randomized encryption, the in-place encryption, for example, is supported. You can encrypt the data basically in the column itself. The equality comparison is supported inside the enclave. Comparison operators beyond equality, like, etc., are supported again inside the enclave. And if the column is enclave enabled with deterministic encryption, the equality comparison is supported outside the enclave, and like, etc., are not supported, right? So the only way to have any kind of pattern matching is by using enclave enabled column with randomized encryption. Now, to fully go into Always Encrypted version 2 is not the goal of this session, and it takes at least an hour to go into everything, how it's all set up, because it's not just a checkbox you tick, but you have to set up like multiple machines with it. It uses outside key validators, key providers, etc., right? Services for making sure that your system works correctly with secure enclaves, etc., etc. So we may do this in a different session. So that's the end of our session, and I'm guessing now now's the time for questions. I thank you for listening to me, and have a